Hello all, I want to welcome you to the third session of a partner training series. This week we'll be covering Algorand Smart contracts, how to use them, and then talk a little about combining them with other technologies. Hopefully this will give you a good overview of when and where to use them, and then we'll and it'll get you started writing some nice applications for Algorand. All right, so to begin with, I want to have a high level, what is a smart contract on Algorand? On Algorand, a smart contract is just a small piece of code, and it's written in our a language we call TEAL, and it's evaluated, and it just returns true or false. That's its primary job. Now, depending on what type of smart contract, it can do some other things too, but the primary job is to return true or false, and I'll explain how that is determined a little bit later in the presentation. But we have two basic types of smart contracts. One we call stateless and one we call stateful. And the primary difference between these two is when they are evaluated and how they're used. For stateless contracts, these are basically what you would typically think of standard transaction approval contracts. Like they're typically used to approve spending transactions. So I supply a piece of smart contract code with a transaction, and if the code executes and returns true, then the transaction is approved. If it returns false, the transaction is denied. And within that category of stateless contracts, we have two types, subtypes. One's called a contract account, which is basically an escrow. You compile this little piece of TEAL code and it produces an Algorand account. Then you can fund that account, and then the logic determines whether anything can leave that account. And we also have something called a delegate contract, which is I want to sign away some of my authority for my account based on this contract. Now, what that might be happen is if I want to set up some type of bill pay where people can withdraw funds from my account. That's the basic two types of stateless contracts. And we have another type of contract called stateful. Now, what it's used for, it still does a true or false, but it also has access to a little bit more of the ledger data, and it also can modify and read and modify a global storage state for that particular contract. You can keep up to 64 variable key value pairs within a global state for that contract. So let's say I was doing a crowdfunding application, I could keep the total amount raised in one of these key value pairs. And then you can also, per user who opts into the stateful contract, you can store a set of values associated with that user for that specific contract. And in the ledger, it's actually stored under their account, underneath their account within the ledger. And you can store up to 16 key value pairs, and we'll get into some more details on that. But the intent for the intent for stateful contracts is to modify state, right? And these contracts live on the blockchain. And what's important to note is both of these contracts can be also combined not only with each other, but with other technologies that we already have to produce these sophisticated applications. For example, I can make a call to a stateful application and group it atomically with a payment transaction. So if either one of those transactions fails, they'll both fail. That's the idea behind atomics. And while stateful contracts currently don't approve spending transactions, they can be kind of made to approve spending transactions by atomically grouping those with a call to the stateful smart contract. So that's the one key area, and you'll see in a lot of the applications that we build, we almost always exclusively use atomic transfers to do things like this, and I'll show an example of that. But as I said, both of these types of smart contracts, they're written in the TEAL language, and that stands for Transaction, Execution, and Approval language. And it is an assembly-like language. It's evaluated one line at a time in a stack engine, and produces either returns true or false. In addition to that, the TEAL code, for some people, the idea of writing a TEAL contract is a little bit daunting. You can always use our project called PyTeal that allows you to write contracts in Python and then compile them down, run a Python on them, and it'll produce TEAL. And then you can compile the TEAL and then use the TEAL, so you don't have to actually write the TEAL. One thing, and I will also say, there's a couple other projects that we're building on top of TEAL that will be of interest in the future. But one of them is we have a team that's working on, I know of at least one grant recipient working on a JavaScript converter to TEAL as well. But I'll discuss some other projects later down in the presentation that may help. But the fundamental goal of this presentation is to give you a solid understanding of how everything works underneath. All right, so moving along. When we're dealing with escrow, this is a stateless contract, escrow or contract account. The logic, the TEAL logic you write, you compile it, and it produces an Algorand account. What this does is it just acts like just like any other multi-sig account, standard account on Algorand. You can fund it, you can spend from it, and all of the standard transactions that you can do with an account. The only difference is anytime something leaves the account, the TEAL logic is evaluated, and if it returns true, it approves the transaction. If the logic fails, then the transaction fails. So, and like I said, you can fund it with assets, algos, all the standard stuff that you would do with a normal Algorand address. So that's basically an escrow contract account's usage. You'll note that anytime a transaction occurs from the escrow account, you supply the TEAL logic. And you'll see when I show you examples of this, how that is done. The other stateless contract is what we call a delegate. And what this does is I can have a set of TEAL logic that is compiled, and I sign that TEAL logic with my account. And what that does is it says, okay, anybody can sign in my name now as long as the logic is approved. So it's a very powerful thing to do, and it can be submitted much later. So say you want to set up a bill pay with your power company, right? You may want to say, okay, you can write TEAL logic says allow this account to withdraw from my account 300 algos every month, up to 300 algos, right, or something like that. Then you could sign that logic, give that logic to that signed logic file to the power company, and then they could submit a transaction against your account and sign it with that logic every month. And you would not even be involved in the transaction at that point. But this is what you call delegating your authority. So it's giving a piece of your authority away to your account. All right, so that's the two primary stateless usage patterns. What some of the types of things that these are used for, obviously for contracts, accounts, escrows, past time lock contracts, split payments, limit orders, things like that. Delegated is recurring payments, or basically anytime you want to give limited account authority to your account. Those are the use cases for that. So that's a high-level overview of what stateless contracts are used for. And do remember though, the logic is evaluated and when it's submitted at the time of when the transaction is submitted. That's when that logic is evaluated, as opposed to stateful contracts, which the logic actually lives on the blockchain and is evaluated during block assembly time. So if looking at this next slide here, we'll talk a little bit about stateful contracts. Another one, we also know these as apps on Algorand. So everybody's probably familiar already with assets on this call, but when you create an asset, you get an asset ID back. Well, when you deploy a stateful smart contract, you get an app ID back. And the way you communicate with that stateful smart contract from then on out is with a new transaction type called an application transaction. Now, there's several subtypes of application transactions. We'll cover that in the next slide. But the primary way, so your logic is essentially living out on the blockchain. You initiate communication with it with a transaction, and you ask it to do something. All right, and you can supply parameters and things like that to it. You'll notice that I have two programs here. That's because every stateful smart contract does have two programs. We have what we call an approval program and a clear program. I'll explain why the difference and why we have two of those in just a moment. But primarily, these stateful smart contracts are going to manipulate state and things like that for every user who opts in, or modify global state. Another thing I'll point out here is if your stateful smart contract does not use any local state, then no one has to opt into the Stateful Smart Contract to use it. There's a limit of the number of smart contracts that you can opt into. So if you have contracts that are not using local state, then there's no need to opt into that contract whatsoever. You can issue transactions against it, and as long as it modifies just global state, then you're good. So, all right, so moving along, we have the two programs. But I want to talk about a little bit about the subtypes of application transactions and what program they actually call within the Stateful Smart Contract. So we have these 6 subtypes or subcategories of application transactions, and they do different things. When someone creates a no-opt call, that's what you would think of as a generic call to your Stateful Smart Contract, and it will call your approval program. And what that allows you to do is that's the standard application call that most people will make use the most. So you're gonna, if you're writing a voting application, the time to vote is going to be a no-opt application transaction. Opt-in is when people want to opt into the transaction. It also calls the approval program. If then we also support deleting and updating application transactions. Now, what these are, this is a little bit different if you're coming from another smart contract language. Generally, a lot of them don't allow you to either update or delete a smart contract. In our case, you actually have to put code in your contract to prevent that from occurring. So, as the creator of the Stateful Smart Contract, I can update it at any time. The only thing I can't change is how much global state I reserve for the contract when I first create it, global and local state. That's the only thing that cannot be changed and is set in stone. And the only thing that can be changed is it can be deleted. That's it. And then we have this closeout transaction. This is anytime as a user of a Stateful Smart Contract, I want to opt out of that. Well, then I can call the closeout, and that'll close my account out gracefully. Now, the problem with that is if that closeout fails, the transaction fails, then I can't get out of the contract. That is why we have the clear transaction. This is a brute force, non-graceful way of exiting a Stateful Smart Contract. And generally the clear programs are very short and just essentially clear you out. This transaction the logic may fail, but the transaction will still clear out everything clear your total participation out of that smart contract. So think of Stateful Smart Contracts as just these things that these pieces of code that live on the blockchain that you can initiate communication with one of these 6 types of transactions. Okay. So, and what are the typical use cases for Stateful Smart Contracts? Well, if you're building DeFi apps like AMMs, lending, those type of things, or crowdfunding types of applications, voting, material tracking, lotteries, seeding, identity restrictions. In that particular case, it's things like, okay, if say I have some KYC requirement, I could do that. I could store that your KYC completement into the Stateful Contract and then verify that you've done those types of things before I allow you to do things like transfer an asset. And essentially, these are going to be, you're going to use Stateful Smart Contracts anytime a global variable is needed, or you need value stored per individual who's wanting to use your contract. So those are the primary use cases for Stateful Smart Contracts. These, some of the key differences between the two is obviously when they're evaluated. When you're using a stateless contract, like I said, you supply the logic every time you submit a transaction that needs to use it. Would block it, and it's evaluated as soon as you submit it. The time constraints are not as stringent at that point, so you get a little bit more computing power available to that particular contract as well, and I'll explain that shortly too. But then and then Stateful Contracts, they're living on the blockchain. They're actually evaluated at the minute as the block assembly is occurring. They both have roughly 1,000 bytes of size limits, and then there's a opcode cost budget for every program, every Stateful or Stateless Smart Contract. The opcode cost is essentially a numeric value that measures how much computing power a specific opcode is going to use. And so typically, like additions, subtractions, those type of things, most opcodes are going to be 1. All right. but there are some more sophisticated ones that require, like if you do an ED 255-19 verify, then that's a fairly significant opcode cost. And the opcode document we'll show you later, gives you the opcode cost for all the opcodes that are available in the programming in the TEAL language. So access to the ledger, you got the Stateful Smart Contracts facilitate asset and account lookups for all kind of things. We'll show some examples of that. When you're doing stateless, you only have access to what's available in the transaction, essentially. So and for obvious reasons, they're stateful ones track state and stateless don't. Logic lives on the chain for stateful, and like I said, logic is submitted with the transactions with stateless. We do have a set of templates for stateless contracts. They're in our reference docs on the developer website. In addition, there are several tutorials on those. You can search the tutorial section and see plenty of those. So this is just a high level, what's the differences between the two. So, I want to talk about, I'm going to walk through a couple use cases of how I would combine combine stateful or stateless contracts together with some of the other technology to solve a particular application problem that I want to build. Just give me 1 second. So the first one I'm going to start with is a permission voting system. All right, let's say I have an app that I want to do a vote between two people, and what I want to do, I want to verify that only one person gets one vote, right? So I'm going to probably use some central authority to enable to basically give you some kind of voting right, and then you can use that voting right to go vote. Well, the way this would be done on Algorand is first you would create an asset called a voting token or something like that. You would allow accounts to opt into that asset, and then we would store that asset later in a stateful smart contract, and I'll show you what I mean by that in a minute. And then I would send out the vote token to all these users. So now they have a vote token. And then the way I would make this work is I would create a stateful smart contract with these. You see things in blue here. These are my global state variables that I would assign with the voting application. I would say, okay, we're going to allow voters to register between these two rounds. Those could be dates, by the way. And then I'm going to have a vote between these two rounds. And then I'm going to have candidate A's vote and candidate B's vote be tracked in global state. And then I'm going to have whoever created the vote. Smart contract. So that's my approval program. Think of that as the approval program. So I create that, I set the registration rounds, set the voting rounds, set the create. And then all my users opt in to the voting app, the stateful smart contract. All right, so and as long as they opt in between the registration begin and end rounds, then the transaction will be successful. If they try to register after the registration ends, then the transaction will fail. All right, so that sets up the stateful smart contract and the asset. The meat of the application is in how do they vote? Okay, and that is using an atomic transfer. The way I would do, and we have an example of this implemented already, but the way we did this is, okay, I made an atomic transaction that consisted of two transactions. One was an application transaction to call my voting smart contract, and the other is in order to vote, I actually have to spend my voting token, and you're spending the voting token back to the central authority that gave you the token to begin with. All right, so those two are atomically grouped. What that says is if either one of these fails, then both fail. When a stateful smart contract fails, any changes it's made to state will be rolled back. So for example, let's say they make a call to vote and they say, I'm voting on candidate A here. And then they don't have a token, so the spending token transaction fails. Then the vote token, the candidate A's vote will be rolled back. So that's the way kind of the failure of stateful smart contracts work. And this is a typical pattern you'll see all through virtually anybody that's going to build smart contracts on Algorand, is they're going to use atomics for things like this. So and also in this particular case, when they vote, as long as it's between the vote begin and end round, then I would cast their vote and they'd spend their vote token. Then you would also store in their user storage whether they voted or not. And then so you could actually double check to verify they ain't already voted or something of that nature as well. But that's what the spending token itself is supposed to prevent the double voting. All right, so that's a general way of how you would combine technologies with Algorand to implement a voting application. So I'm going to do another one and talk about crowdfunding. All right, so in crowdfunding, what the whole goal of a crowdfunding application is, someone creates some fund that some program that they want to fund. All right, and they set a goal for that, and they set a end date by which they want to make that goal. And people give to the fund. If the fund at the end of the end date has not reached its goal, then the people can get their money back. Else the initial receiver of that fund gets the funds that they raised. And so to implement that on Algorand is fairly simple. You create a stateful smart contract that has these set of global state variables: the fund start date, the end date, the fund goal you're trying to reach, the current fund amount that you've already raised, an escrow address to hold all of the escrow funds that are donated, the creator of the smart contract, and then who is the intended recipient of the fund, and then a final fund closeout date that you can clear all the funds out that are not being claimed. All right, so in the case of how I would create that with a goal app creator using the SDKs, I would also create a stateless smart contract that referenced the specific application ID, and so it essentially links the stateless and stateful contracts together. And I would update the stateful smart contract to increment to store the escrow address in global state. So that's essentially a way. 1 and 1A are just ways of linking the two contracts together. As now, you remember when you compile a stateless contract, you get an address. Well, that address goes back into the approval program. Well, the stateless contract may want the application ID, so you have a chicken and egg problem. So the way you do it is just update the contract after you've deployed it. That's one way of doing it. There's other ways of doing it as well, but that's the way I did it in this particular case. All right, then what in order for people to donate, they have to opt into the contract. And the reason being is because we need local state to store how much they've given. So as part of the donation, when you donate to the escrow, you also have to make an approval on a call to the stateful smart contract saying saying you're donating to the fund. And as long as it's before the fund end date, then the stateful smart contract call will be approved and the payment will go into the escrow. So it's atomically done. Now the meat of it is, how do you handle payout? So what you do is, the way you handle payout is, at the end of the fund end date, the intended recipient, if the fund goal is met, the intended recipient can make a call to the contract saying, hey, I want to collect my funds. And in the same moment, they would also submit a payment transaction from the escrow to themselves. So those are the two transactions that would have to be grouped. And like I said, the fund escrow only spends when it's grouped with a call. That's built into the logic of that particular stateless contract. It says, I will not allow any funds to leave this account unless they also call this specific application at the same time. So that's a way of linking the two together. So that would be the payout fund, right? And then in step 4 here, this is if your fund doesn't make the goal. Then what this allows is you to atomically group two transactions for anybody that donated to receive their funds back. So what they do is they call a call to the crowdfunding smart contract and say, hey, I want my money back. If the fund end date's past the end date's past the fund end date, and the goal amount is less than the fund goal, then they can get their original donation back. And you do things like make sure that you're checking that they're not trying to ask in the payment transaction more than they actually gave. Things like that are going to be in the approval program logic. So that's in this particular case, in the first example, we used assets and atomics and stateful smart contracts. In this example, we're using atomics, we're using payment transactions, and we're using stateless and stateful contracts. So this is a way of combining all the pieces of technology. Next week, we hope to show the examples you're going to see today are fairly simplistic in nature, but so for next week, we're hoping to show some of these, how we actually built some of these apps, and show you some sample code, and spend a lot more time in getting our hands dirty and showing you the way things were built and how you can combine these pieces of technology. But this is just a high-level overview of 2 applications that we've built and how we built them and how we combine the technology pieces. All right, so let's talk a little bit about runtime architecture. Okay, and I'm gonna talk about if you think about TEAL, that's the transaction execution approval language. This is a language. Something has to evaluate it. You know, some type of TEAL VM. We call it a TEAL interpreter, right? So where that interpreter lives and how it processes your program. That's what we're going to discuss here. Starting with stateless, what you do when you first initiate a transaction that's involving TEAL. So that means if, okay, let's say I'm using an escrow and that's my TEAL program, and I want to send a transaction from the escrow to someone else, then I have to supply the TEAL program for that transaction. Additionally, I supply some arguments. I post these to a node. The node has the TEAL interpreter embedded in it. It has a stack. Like I said, it's a stack engine, so it processes your TEAL program one line at a time. And it has access to a set of global variables and some transaction properties that it can use to determine whether this is going to return true or false. Additionally, we have this scratch space where you can write temporary variables for storing things that you want to reuse and you don't want to rerun the same calculation, that type of thing. So that's the stateless TEAL runtime architecture. Another way of looking at it would be this. So I have my program, and we'll get in. Don't worry about what's in the program yet. We'll talk a little bit more about that in a minute. And I have a stack, and I have a scratch space, and I have a set of arguments that I pass in that are passed into the stateless smart contract. And I have a list of transaction properties that I can go get. I can go look at, like transactions amount, the receiver. If it's X for asset means what asset is being transferred. If this is an asset transfer, those type of things. So I have a lot of leeway on the types of values that I can get in. Note that those are read-only. You cannot write those values. Now let's talk about stateful contracts and how they're architected. Their runtime architecture looks a little bit different. In addition to passing per the transaction, in addition to passing arguments, you can pass 2 other things associated with it. You can pass what we call foreign applications, and this goes into what we call an application array. Now, what does that mean? That means I want my think about it. If you're at, think of a stateful smart contract in our vernacular as an application. So, if I have an application array, this allows me to essentially pass in 2 additional stateful smart contracts into an array, just their IDs. All we need is their ID. Put those in an array and pass that in the transaction. That allows me to go out and read their global state within my current contract. Now I cannot modify that global state, but it allows me to go out and read their global state. And I'll show an example of that shortly. And then we also can pass in this thing called accounts array. Now what this allows me to do is every stateful smart contract can access up to 5 accounts, the sender of a transaction plus 4 additional accounts. And what they can do is look up things like your local state for a particular contract. They can look up your balance, your asset balance, any of that. So anytime you want to reference another account's values, you have to pass those accounts into in the transaction. It's important to note too that you can change these accounts every transaction. So you could do multiples. If you wanted to route through, say, 10 or 15 accounts, you just make multiple transaction calls. And then in addition to that, you can actually modify the local state for any of those 4 accounts, any of the 5 accounts total. You can modify local state for whoever sent the transaction, or the 4 additional accounts that are passed in. The difference is the TEAL code is already, when you deploy it, the TEAL interpreter is actually on the blockchain itself, and all the nodes, and it actually is you're not passing in the logic. You're just saying, I want to call this Stateful Smart Contract ID. This is the programs are loaded into Ledger soon as you what we call create, right? A create transaction for these, and I'll show you how that's done. But then we have a stack, same way, process one line at a time, access to global variables and transaction properties, much like stateless. But in addition to it can read and write global and local state. Now, and there's some, if you're using the application array, you can actually read global state from other contracts. And with the accounts array, you can read local state from other contracts as well as your own. So I'll show you a little bit about that a little bit later. But those two arrays are very important when understanding how things work in your program. So I'll show plenty of examples of that shortly. All right, so that's the runtime. Another way of looking at it is similar to the previous one. Is this you can you can pass up to 2 stateful smart contracts to reference, up to 4 additional accounts. You have access to 64 KV pairs in global state, 16 KV pairs per user for local state, and these are 64 bytes that can store ints, UINTs, and byte arrays. Those are the 2 types that you're allowed to store in the state. All right, and so that's the essential architecture for basically the stateful smart contracts. So let's talk a little bit about what language you use and how is it processed and some of the opcode support and things that are out there. The intent of a stateful smart contract is to return true or false. How does it determine that? Well, if it's TEAL is a byte code based stack language, meaning it just processes one at a time, and we've got pushes and pops that happen, and we have opcodes that operate on that stack. And what they do is they'll pop some values off the stack and push another value on. I'll show you an example of how all this works. And probably the best way to see how TEAL works is actually using our debugger, and I'm going to show that in just a moment. But so we have we determine whether a contract returns true or false based on whether there's one positive value left on the stack. If you leave a 0 on the stack, then it'll return a failure. If you return 2 positive values, it will return a failure. The only way a contract returns true is if there's only one value left on the stack and it's positive. It's greater than 0. So, and then we have full, by the way, we do have full SDK support for deploying smart contracts, both stateless and stateful. I'll show a couple examples of that shortly, but we'll get a lot more into that probably next week. I'm primarily going to be using Go. That said, and I will tell you one of the reasons I do that is anytime I develop a smart contract, I want to make sure the contract's logic is solid before I hook it up to my UI or any of the higher order languages. So I'm actually just using Go most of the time in a private network to debug my smart contracts. And like I said, with these, we have over 70 opcodes, and they operate on the stack and they push and pop values off of it. We'll show examples of that. They have access to things like ASA, algo balances if you're in stateful. And if you submit an atomic transfer within your TEAL smart contract, you don't only get to look at the transaction that called your smart contract, you get to look at every transaction in that group. That's what makes it powerful. And then I can also, with stateful and modify state, we have opcodes for that. We have opcodes for signature verification if you're in stateless. And then obviously we have this PyTeal library that compiles down to this language if you don't really like writing the stuff. But when you see a couple examples, you'll see that TEAL is not all that complex. It sounds scarier than it really is. And it takes very little time to get used to. So let's talk about a little simple example. Let's say I have this program, and this is a TEAL program that's just 3 lines long. Now, you please understand that these are examples I'm showing you should never be used in production. These are for learning exercises only to help simplify the way the language works. The first transaction is using what we call the TXN opcode and pulling out the value amount. Remember when I said you can get all the transaction properties? So that's just saying, give me the amount, load that onto the top of the stack. So that's what it does. It pushes the current transaction it's processing, its amount on the top of the stack. Then the next opcode, int 100, is int's a pseudo operator that a pseudo opcode that basically acts as a helper method. It's going to push 1,000, the integer value 1,000 on top of the stack. So now that top of stack transaction amount gets pushed down. The third thing is the opcode greater than or equal to. Now what this does is it pops the two top values off the stack and compares them. If the transaction amount is greater than or equal to 1,000, it pushes a 0 or 1 on the stack, depending on the results of that check. We have every opcode documented on what it does to the stack in the opcodes document. I'm going to go to that in just a minute, but you'll see here. So what does the opcode do? It pops the A and B off the stack and pushes a uint64. In this case, it'll be 0 or 1. And so it says A greater than or equal to B, then push 0 or 1, right? That's the intent. Actually, that should be reversed. No, actually it is reversed. All right, so that's every opcode's defined like that. Most opcodes will have a cost associated with it down at the bottom. If this opcode does not have a cost, assume it's a 1. So that's a 1 opcode cost. So and if I'm in the stateful smart contract, then I can do 700 of these as a limit. And you could do 20,000 of these in a stateless contract. All right, so and another thing too is not all opcodes support both stateful and stateless. Some opcodes are only available in stateful, and some opcodes are only available in stateless. For example, app local get, that gets the local state for a particular account, a local state variable for a particular account. We use this term mode : application. That says it's only valid for stateful smart contracts. If the mode was signature, that would apply to, that would mean stateless contracts. So that's what essentially TEAL and Stateless acts like, basically a signature for transactions. So that's why we use that term. So, and if you, the opcode reference document, you can look here, it's got them all. And there's plenty of them to do, but like things like, I'll give you an example, ED 255.19 verify. This is if you want to verify a signature, right? That is not allowed in application. It's only allowed in stateless, and its opcode cost is 1,900, which is more than the total budget you would have for a stateless contract, because it's a very expensive operation. All right, so you can take a look at these. They're all defined there. We're going to go through several of these and talk about what they do. Okay. All right. So as I said, we have a set of, you already saw one pseudo operator. We got several of them. If you look, we got like int loads an int, byte loads a set of bytes onto the stack. Like in this particular case, byte my string, that loads my string onto the top of the stack. ADDR is a pseudo operator for converting an address properly for the stack engine. You can see what it's doing there. So this will load this particular address. This is all this piece of TEAL code is doing is comparing the transaction receiver to a specific address and seeing if they're equal. Okay, those are our pseudo operators. So as we've talked a lot about the stack engine, I want to show you how the stack engine works, just so you can get an idea. And this truly is the best way to learn TEAL, is to make sure you set up your debugger and get it working. All right, so if you look here, I have, this is a standard way I showcase TEAL, is I start a private network, and I actually have that up here. I just have a couple scripts that use a little private network that I have my network template here, this couple wallets, and then 2 nodes in this particular network. All right, and then I've got stopnet and startnet, which basically start and stop my private network. All right, so the first thing I want to show, let's go ahead and start this network up. I got this one open here. Okay. And the first one I want to show is this create, let's see, create global. Yeah, so this, what I'm gonna do is I'm gonna create a stateful smart, create a stateful smart contract. And the way I'm doing this is when you see GCMD, that's just a pointer, a path to my goal. So it's just think goal app call. What that does is creates an application transaction. And what I'm doing is specifying an app ID. That's actually in debug. Let's look at the create for that. All right, so this is actually where you create it. So goal app create, that creates an application transaction for creating the Stateful Smart Contract. As part of that, I have to supply who's the creator of it, the approval program, that's my atomic TEAL, and I'll show you what that looks like in a minute. How much global and local storage are you planning on using? Now this can be these in total can be 64 total, and with local byte slices, those can be in total 610. Once you set this and run the creation of that Stateful Smart Contract, that's it. You can never change that size. The only way to change that size is to delete the smart contract and redeploy it. And then also I have to supply my clear program. Okay, so these are the two programs I've got for this particular example. Let's show you what those look like. Here's my global. All I'm doing here, and I'll show you this in the debugger, but it's just getting this global variable with using app global get and incrementing a number, and then just storing it back. Very, very simple. The clear program is even simpler. All I'm doing is returning int1. That means this will always return true. Okay. All right, so going back into the debug, first thing I'm gonna do is let me run this create global here. Create app. Okay, so that's all that is doing is deploying that Stateful Smart Contract. Now it is on my private network. It's out on the blockchain, and I get a transaction ID. And echoed up out the account. So next thing I'm going to do is debug that. Like I said, this is where I'm actually making a call against this, a generic call. I'm passing a couple arguments. One's a string, one's an integer. This is from this account, and then I'm dumping it out to a file and using this thing called dry run dump. We use this, so you essentially, what this does is pull all the state that you're required to debug and dump it to a file. And it's not actually submitting this transaction to the network, but it's saying this is what would happen if I did. So it pulls all that data down, puts it in that file, and then you can run this TEAL debug, debug, and then the name of the program, and then specify the file you want. Now I'll show you what that does. So debug global. Let's show. Oh, did I mess up? I must have did something wrong, man. Let's try that again. Okay, there we go. All right, so what this does is starts the debugger in listen mode. It's waiting to be connected to from the Chrome debugger. If I go to Chrome inspect, that's all I do is just type Chrome inspect in there. This will show up. You may have to configure it. If you go to the developer website under TEAL, there's a debug document describing how to do it. Heck, I'll show it to you real quick. So if I go to explore features, smart contract debugging, this will tell you how to set up the debugger. But if I click inspect, launches the debugger. Now this is the TEAL code for that Stateful Smart Contract, and this is the transaction for that particular call. In here, I have things like, here's my global state. You can see the counter sitting at 1. I have my group of transactions. If there was a group of transactions, my scratch pad space. Most importantly is the stack, because this is what you'll spend most of your time in when you're debugging, and then the transaction, and then also a set of global variables that I can, that global set of variables available to the contract. All right, so main thing is look at stack, as I said. Right now, the length of the stack is 0. All right, so I'm going to start debugging one line at a time by stepping through this. First thing it does is it's going to use this the byte pseudo operator to push the string counter onto the stack. You can see that's what it's done. It's on top of the stack. Next thing I do is we're calling this app underbar global get, which says go out and it pop off the last value off the stack and put back on the stack the value of that global variable. So you'll see here, all it does is pop off counter and returns 1. That's what the current value is. Next thing, I'm going to use the pseudo operator 1 and push that on the top of the stack. Now we have 2 1s. The plus operator is going to pop both of those and push the combined value of those back on the stack. So that's where we get into it. Now I store this in a scratch space, and the reason I'm storing it is because the order you pass the arguments for an opcode matters. And in the case of, I want to now write this new updated value back to global state, I have to first supply the name of the variable and then the value I want stored. So that's why I store it into a scratch pad and load it right here on line 12. So first thing, push counter on the stack, load 1, so it loads the 2 that we just calculated. And now I'm going to, the app global put pops both of those 2 values off the stack and pushes the result of that put. I mean, it doesn't push. No, it actually doesn't push anything to the stack. It just writes the value. And then the last thing I'm going to do is, since if I were to return right now, this would be a failure because there's nothing on the stack left. So I want to load up the last value. As long as it's a positive value, then it'll return true. And then I return. So that's essentially a walkthrough of the global one. I want to show you real quick on another example. Stop it and start it again. The reason I'm stopping and starting it because I don't want to have to update the scripts every time with new application IDs, because that would be different every time you created it. All right, so the next one I'm going to do is do a branching example. App branch sh. All right, so this is creating. I'm just telling you, this is just creating an app that's got some logic in it. I want to show to you. That's very similar to the way I just created the same app, created the global one there. Okay. Debug branch. All right, so this is another TEAL program. I'm in the debugger, and it's just a simple program that does some checks. And the main thing I'm showing off in here is branching. While TEAL is not a Turing complete language, meaning you cannot loop in it, but you can branch forward. All right, so there's 3 opcodes that allow you to branch forward. There's B, BNZ, and BZ. BNZ says if there is a positive value on the top of the stack, then branch to the label. If not, then just keep going. If the BZ says if there's a 0 on the top of the stack, bounce to this label, else keep going. And then the B opcode just says always branch to this label. And if you look here, you'll see this on line 6. We got BZFIN. That says if the 0 is on a stack, the top of the stack, bounce to the fin label, which is down in line 21. And that essentially just loads a 1 on the stack and returns. Another thing that the BZ, the BZ, and the BNZ opcodes do is they pop that value off the stack. So I'm going to walk through this and show you that as an example. All right, so this thing, I'm looking up a transaction property, looking for the number of app args. This has I used essentially the same call I used in the previous debug session, which means I have 2 transactions. So number of app args says in this transaction how many arguments were passed, and so I'm looking at the stack and it says okay that was 2. Now I'm loading int 2 on there, saying are those 2 equal? And if they are equal, then if those weren't equal, we would bounce to fin and the program would return true. But in this case, since I'm using BZ, it's saying only bounce if there's a 0 on the stack. Then it's going to go right by that. So you'll see it steps into that. We load the string myArg up, and then I'm comparing that to my when you say application args, you're saying give me the application args array, and I want the first one is the 0th element in there, right? So in this case, it's going to be the string myArg. That was the argument I passed. Then I'm comparing to see if those 2 strings are equal, and now I'm doing a B and Z check second arg. This is going to drop me to here, and that's what it does. All right, and then I'm going to look at the second argument. And so I'm loading that up. Now this is interesting because this is not what I passed in, but when you do that's the way it comes in through a byte array. And then when I do B to I on it, then it converts it to the integer that I'd actually passed. So I got a byte array that's using the B to I opcode. And then what I'm going to say is load up 100 on the stack and say, all right, is the second application argument greater than 100? That's all this is doing. And if it is, then I bounce to FIN, which is what it does. So that's the way the branching works in Algorand. No, like I said, no Turing, no going backwards, but you can go forward, at least for the time being. All right, so and I showed you the state demo. I also showed you the B and Z and BZ functions, or at least discussed them. Let's talk a little bit about that. These aren't all the properties in the transaction because there are some that I actually missed under my list here, but these are the types of transaction properties that you have access to. And it's simply all you gotta do is type in TXN and then the property that you want. And that's the list of properties that you got. And then in this case, I'm just saying transaction amount is greater than or equal to 1,000 microalgos. I also have access to a set of global variables. Now, not all these global variables are pertain to both contracts. Specifically, if you look at things like latest timestamp, what that is the latest timestamp of the previous, when the last block was confirmed. That's as close as you can get to the time on it. And that is only available in Stateful Smart contracts. Group size is how many transactions were submitted at once in an atomic transfer. The zero address is basically a way of saying that a certain address is not set, and you can, and so we call it the zero address, and so we have this global variable for it. And then you got minimum balance, minimum transaction fee. Another thing you can get is current application ID. I want to know what my ID is currently in the Stateful Smart contract. Some other things you can do is you can actually check the type of transaction, and this is useful every time you're in a Stateful Smart contract. It's always going to be APPL for the call that's processing the Stateful Smart contract. But if you're grouped with other transactions, you may want to check the other transactions properties. Well, you can do that by using the type enum field, and in this case, in the constant name. So TXN type enum would load whatever the type of whatever the current transactions type enum is. And then if you put in APPL, it'll load the integer value for that particular one, so that and comparing those two will allow you to say, okay, this is a payment transaction, this is an application call, those type of things. All right, and then not only can you check the transaction types, but if it's an application transaction, you can actually check the subtype. Remember the 6 we talked about earlier? So I can just do using the onCompletion transaction property. So I can say TXN onCompletion no op equal. That what that says is this a no op application transaction? Or is this a closeout transaction? Is this an opt-in transaction? Right, so you can compare the two. Now let's talk about atomics. So atomics allow me to group, like I said, group multiple transactions together and submit them at once. In TEAL, I can use something global called group size to actually determine how many there are and enforce how many I want that should be there. Let's say I'm expecting 2, then I can put, if those 2 aren't equal, then I can just return off. If the group size is of 2, I can just return a false immediately. Right? In this particular case, this bit of TEAL here says, okay, the first checks to see if there are 3 transactions in the group. Is the first one a type of Stateful Smart contract call, and those 2 conditions together? Then I'll have a 0, 1 left on the stack. Then I say, okay, the second transaction, is it a payment transaction? If it is, I end that in, and I'll have a 0, 1 on top of the stack. And then the final one, it says check the third transaction, is it an asset transfer? And then combine all 3 of those and end those together. So that's essentially just a way of enforcing, okay, these are the types of transactions that are in it. Obviously, you'll check other things like, is it the proper receiver? Is it the proper application ID? All of that kind of thing too. But this is a simplified thing of checking the atomic transfer. So let me show you a quick demo of that. Okay. So I'm gonna stop and start this network. And I'm going to create the atomic one. All 3 of these do the same thing. I just didn't want to modify code in shell scripts while we were running this. So, and you see, remember when I was doing the 2 arguments, you can see app arg, my arg, and then the integer value there. All right, so and in a minute, I'm going to show you how you call some of this from the SDKs as well, just so you know. All right, so now let's debug that. One thing I'm going to do is explain what's actually happening here, because there's a lot. When you're doing atomics, and especially if you're using Gold, it's pretty simple to do using the SDKs, but with Gold, it's a little bit more complex. You see, these are two transactions that I'm doing, transaction 1 and 2. One's a call to a stateful smart contract, mine, and then I'm doing a payment transaction to this account, okay, at an amount of 500,000 micro outgoes. I have to write up both of those up to a file, then add them together, and then what we do call group. Then we got to split them, sign each one of them individually. Generally, those will be signed in different locations. Then you cat them both back together and submit them to the network, or in this case, submit to a dry run, which is what I'm doing here. And then I'm setting the group index here for the debugger, saying, oh, I want to debug the first transaction in the list. That's the one I want to debug, which happens to be my Stateful Smart Contract call. So that's what this is doing here. All right, so if I bounce into this, look at the inspector, you'll see here's my atomic one. And there I have my group of transactions that shows 2 transactions, and here's my stack. So first thing I'm going to do is, okay, one thing I want to state here is this piece of code, lines 2 through 5, this is a common way of determining whether in your TEAL code, is this when I'm being created? Because your TEAL approval program actually runs when someone tries to create your Stateful Smart Contract using that TEAL. So the only way to know whether you're truly being created is to check your application ID. So by check the transaction application ID, if it's equal to 0, then I know this is, at this moment, this contract is being created. I should not be executing any additional logic on it in this particular case. You may want to do things at creation, but this one didn't need to do anything. So if that's true, then I'm going to bounce to creation and return a 1 here and approve that transaction, so it'll actually deploy my Stateful Smart Contract. The rest of this logic is for actually any other type of call that's associated with the contract. So in this particular case, since we've already created it and this is the second call I've made against it, this logic is going to give me a different ID. So if I look at my stack, I push a 0 on the stack, and then I'm going to look at transaction application ID, where you'll see my transaction ID is 1. Now, if you do this on testnet, it's going to be some massive number. It won't be 1. The only reason it's 1 is because I stopped and started a private network. Now I'm going to compare those two. Well, they're obviously not going to be equal. And since they're not equal, B and Z creation won't branch to that. So we're going to go to the next thing. I'm going to pull this global variable called group size out. So if I push that on the stack, it says, okay, we got 2 transactions in the group. Let's verify there are 2. Equal compares those 2. Leaves a 1 on the stack. I'll check the first transaction. Is it a Stateful Smart Contract call? That's int value of 6, by the way. So it's comparing those 2. Yep. And ANDs those 2 conditions together. You notice how I keep ANDing the conditions together, shrink it down to only want to return with 1 value on the stack. That's the whole goal. All right, the second one is a payment. Check and see if it's a payment transaction. ANDs that. It is. Third one is I'm checking the amount. And notice I'm using GTXN right here, right? So the difference between when you're doing atomics, instead of using TXN, you use GTXN. And then you get to specify 0 through X, how many transactions you got. Typically, if I wanted if this was just a single transaction, I could say TXN amount. But in this case, since it's a group transaction and I'm looking at the second transaction, then I'm going to say GTNX, index, and then the property I want. So in this case, it's second transaction and I want the amount property. So I'm loading that on the stack, and it's 500,000 micro algos. Is that greater than 10,000 micro algos? The answer for that is yes. So and those 2 conditions together, and I'm left with 1 on the stack. I can return at this point. So that's the idea behind that. I want to talk about a few other pieces of things that you can do. With a call to a Stateful Smart Contract, you can check asset balances. And this is key for okay, I don't want somebody to be able to do something unless they own this particular token, for example, right? Like in the case of the voting application, I want to verify they have 1 voting token, or at least 1 voting token. So the way you do that is you call this opcode called asset _holding _get, and specify that you are interested in the asset balance field. The only reason you can do this is because you can, because this is a stateful TEAL application and you're looking up ledger values. The first parameter to that call is an integer into the application array. Remember we talked about that application array early on? The index, this is the index into that. Int 0 would be the sender. Int 1 would be for the first passed in additional account. Second passed in would be int 2, and so on. And the second one is the asset ID that you're interested in looking at. Okay, so I'm checking, that could be anything on the system, any asset on the system, because everybody, an asset ID, an application ID's local state, they're all stored in the ledger underneath a user's account. So you pretty much can get access to anything for those 5 total accounts. So in this case, you just pop that asset holding get asset balance returns 2 values. It returns at the top of the stack whether it's true or false, that it found it, so it'll return a 1 or a 0 if it found it, and if it did find it, the second value below that would be the actual balance. So in this case, I assume that I'm doing a pop, which just pops the top value off the stack and throws it away. I'm assuming they already have the asset, and then I'm comparing that to, is it greater than or equal to 1? That's how you can do they have this particular token in their ledger, in their balance. Okay, I can also do things like read, like I said earlier, is read the state of other contracts. So you may have one master contract that has some hard value that's rotating over time based on something, right? And then you may have other contracts that want to derive some value off of that stateful smart contract's global variable. Well, then it's a simple, you just pass that global contract into any call to the derived contracts application array when you're initiating a transaction. And that allows you to actually read that global state. You can't modify the global state from the master contract. Let me show you an example of that real quick. So let's say I have, let me go ahead and stop and start. All right, let me go ahead and create it while I'm going to talk about it. Create app master. Okay, while that's creating, so in this particular case, I'm creating two smart contracts, a master one and a secondary. All right, forget about the byte slices and all that right now. Just concentrate on those two. My master and secondary TEAL. If you look at my master, it's quite simple. All it does is write the value 5,000 for master value and puts that in the global memory and returns 1. So very, very dumb contract, doesn't do much. All right, the secondary, it's going to want to reference that. So same call as before, except here I'm putting, I want, instead of int 0, which would be the sender's value, or would be the current application, I'm putting int 1, which says give me the first passed in additional application. And in this case, that it's looking for, this should be the app ID of that smart contract. You go, okay, I want the master value, the byte, the key master value, and this app global get ex looks that up. Yeah, you notice I'm doing a BZ failed here. What that says is, as I said, it returns 2 values. The first one on the top is going to say, did the call opcode return a value? If it didn't, then I'm failing out of the contract at that point. So let me debug that real quick. Debug. All right. So if I go into inspect, you'll see that I'll just go ahead and well, here we support breakpoints with the debugger, so let me just play it up to there. All right, so let's leave this on our stack. Right now we have nothing. I'm going to load an int 1 that says give me the first additional app in the app array, and I want its current global state value for master value. That's what that app global get ex does, and it pops both those values off the stack. All right, and it returned 2 values on the stack. The first one would be the whether it's true or false, whether it actually found a value, and the second one is the actual value. And now I'm just going to compare that to 5,000. If it's equal to 5,000, then I'm going to say if it's not equal to 5,000, I fail. Else, I'm just going to load 1 on the stack and return. Fairly simple stuff. All right, so it returns. All right, so that's that one. Okay, let's talk a little bit more about read and write local state in the accounts array. When you pass in those accounts, here's 3 snippets of TEAL code that do different things. But the first 2, if you think about it, the first 2, they read and write local state and for a particular user, the sender account. So that's where you're saying app local put and app local get. Those are the 2 opcodes that actually write local state for the sender. Okay. You can, and what this also allows you to do is, if I have int 1, then that would be the first additional account passed. Int 2 would be the second additional account, and then I can write any of their 16 kV pairs in local state. So that gives you, not only can you modify the local state for the account that sent the transaction, but up to 4 additional accounts. This one makes this particular set of opcodes quite powerful. In addition to that, the final snippet of TEAL down there at the bottom is using what we call app local get ex, which is a little bit different of a function. If you look at app local put and app local get, they don't return 2 values. They just return the value, or in the case of app local put, it returns no value. But in the case of app local get ex, it returns whether it found a value or not, right? So in this particular case, so not only can you specify the account, but you get an extra parameter that says what contract are you interested in. So I can say, go give me the local state's value for this particular contract for user account 1 or user account 3. And so that particular call gives you that kind of power. So not only can you read and write local state for the sender and multiple accounts for that specific smart contract, but then you can also read existing, read any other contract in the entire ecosystem and read its values for those particular accounts, which is nice. So, all right, we've talked a lot about stateful contract. I want to show a little bit on showing an escrow and how we could possibly use that. So here's an escrow account. Don't worry too much about it, except that all I'm comparing is I'm allowing funds to leave this escrow if they're being sent to this particular account. All right, and then I'm making sure that the fee's not too high, and then some standard checking for the things like, oh, I don't want to make sure this isn't a rekey operation, transaction, or closure magnitude, or something like that. And then I'm also verifying there's only 1 transaction, so it's not grouped with anything else. All right, so when I compile that, watch when I do this. If I go, pardon my goal pathing, but if I type go clerk compile, all right, so notice it gives me this address. All right, so I'm going to try to, what I want to do, this is my contract address. I can fund it. Well, the way I would do that is I'm just going to say, okay, send some money from this account to the escrow account. Notice I'm using that same address there. And I'm going to send 500,000 microalgorithms. Then I'm going to try to send funds from the escrow to this account. The way I do that is in TEAL and goal is just say from program and then give it the program. That's all you have to do. And then specify the amount. In this case, I'm outputting the dry run so I can debug it and show you how it works. So let's run that. All right, and you'll see here, this is evaluating. Now, keep in mind, it does get evaluated at a different time, but same basic process. All right, so I'm gonna check to see if you look here, there's who the receiver is. When I do the ADDR, that's the pseudo op converts it, so they're the same. They are the same, and then I'm checking the fee to see if the fee is less than a certain amount, which it was, and in those 2 conditions together, and then doing just some routine checks and just ending these one at a time, right? That's all we're doing here, and that should return true. Yep, that was it. So that's a fairly simple example. But wanted to make sure that you understand that there's not a whole lot of difference in the way you debug them, and it's pretty simple to do. All right, so let me go back to here. Okay, now I want to talk about, I'm going to actually show 2 examples. I'm going to talk about using the SDK to to do a delegate demo. And the reason I chose this particular one, first off, I had a problem this week that I needed to use some code like this, and I thought it'd make a good example. But I wanted to show you how you would take take TEAL, compile it, use it in a particular transaction from one of the SDKs. And we'll show a little bit more of this next week. But here is I'm just connecting to Sandbox. Ryan covered Sandbox, very simple to connect to. And the nice thing is you can always, all our samples can always be the same thing, and they're always going to be connecting to this. This wait for confirmation is a function that just we wrote to basically wait on the system until it returns whether the transaction succeeded or failed. Don't worry too much about that. Here's the important part. So first off, I connect my client, and then I'm recovering a mnemonic. Never put your mnemonic in your source code unless it's for testnet only, because this is not a safe thing to do. But in this particular case, I'm using the file system module to load up this sample.teal. And sample.teal is a piece of TEAL code that just returns one. Please never use this in your production environment, because this essentially gives away all authority for a particular account. So go back to that. All right, so all I'm doing is loading that TEAL up. The whole idea is just to basically show you how to compile. Now you do have to set whatever node you're connecting to has to have a server variable turned on, and you can read about it. Look at when you go to the SDK pages. There's that'll explain the variables that need to be set. But but I'm doing this using the client to call the compile method. And this is a REST API that you're passing the actual TEAL to. So it compiles it and it returns it in base64. So I reconvert that to UN8 array and call that my program. Now, this is a standard way of creating what we call a logic sig. A logic sig is nothing more than a piece of logic that can be used to sign stuff with. And this is the structure that they have to be placed in. All right, so in this particular case, I'll say make logic sig with the program, and I got this lsig. Now I have a couple choices here. If I'm using it as a delegate, I can go ahead and sign that logic with my account, and that's how I would do this right here. And then I can take this lsig and I can write that out to a file and give it to somebody else later, or I can use it immediately. If this was an escrow account, I would not do this sign here. I would change the sender of a transaction to be lsig.address, because then that says, okay, this transaction is coming from this logic. But in this case, I'm using it as a delegate, so I sign that logic. And then now if I want to use that logic, then here's just how we get a set of suggested parameters. Make a payment transaction here. This is standard stuff that's been covered before. Then I'm going to sign that transaction. Here's transaction. I'm signing it with a logic sig. That's what this method does. And I'm passing the lsig that's associated with that. Next thing you know, I just push that transaction to the server, and then I wait to see if the transaction is confirmed. So to run that, all right, it's running, and then you'll see that it confirms. Confirmed in that round there. Okay. And by the way, that my sandbox was set up for testnet. All right. I also have another similar example that just shows you how to group those two. So you can just assign the group. So this is a group transaction, creating two transactions. One's a payment transaction, one's signing with the logic sig. Concatenate those two together, and then sending those transactions. I'm not going to demo that particular one. All right, the other one, and I'm not going to run this one because this one actually takes quite a bit of time to run, but this is a sample that's already out on the developer website, but is basically shows you how to do everything from a stateful smart contract. It's probably going to be the most important one you're going to use as far as learning to create stateful contracts. So there's a whole set of functions that Ryan wrote this example that show you how to do things like compile a program. That's how it's essentially the same way, except you got to compile both programs, and here's how you create one. And in that create app, let me go to its actual definition, this is where we're creating a transaction, right? So there's, let me show you where it's at, right here. This is a maker function for creating that transaction. I'm saying this is my sender, these are the parameters. On complete, and then right here it should be a no-op. That's what we're calling that as a no-op. So that's the subtype of transaction we're doing here. And then the approval program, the clear program, and how many integers and integer local ints, local bytes, and global ints and global bytes that I want to use. And then sign that transaction and send the transaction and wait for it, right? So Ryan's created one for opt-in. There's one for just generic calls to it, like and that's going to probably be the most predominant type. And he shows how you can, how you would use the client account information to read local state, and same thing to read global state. So as these variables are in there, you don't have to make a call to the Stateful Smart contract to actually go out and read the state. You can just use the account information REST API to actually go get the state values. And then here's the way that he's got an example for updating the app and closing out the app and so on, deleting the app website, and then finally clearing out the app. I think that's the last one in there. Yep. All right. So you can step through that if you want to and try to get an understanding of that, but it's fairly straightforward. Hopefully we'll show a little bit more examples of this next week of actually using the SDKs, not just in Go. But like I said, the main reason I use it in Go is so I can debug, test, and make sure my contracts are really tight before I hook them up to the rest of my web app. In fact, I wrote a DEX example, and you'll notice I have a DEX example and a DEX web app, because one is just for doing the contract, and the other one is for hooking it up to a web app. And I'll probably showcase this web app next week. Okay, so that said, I think we're getting close to close. I will say we got there's a library called PyTeal I told you about earlier. If I have this particular TEAL, this particular Python, I can, and all this does is basically has 3 conditions, and these 3 conditions are defined here. This right here says and those 3 together, and the rest of this is just so I want to compile the program and push it out. If I run Python 3 on that, it'll produce this TEAL, which is just those 3 conditions anded together. So the PyTeal, PyTeal has that, and if you look from an example standpoint, it's pretty straightforward. Here's that same PyTeal. Here's my 3 conditions. I'm anding those all together. So to run that, I just go Python 3 PyTeal slide.py, and you can see it produces my TEAL, which I can then use in any of my programs or compile it right there, or whatever I want to do. So PyTeal is a really nice feature. It's completely documented on the PyTeal documentation site. You can get to that also from our site as well. So just go down and look for PyTeal under Stateful under Smart Contracts. Another thing I want to talk about, and we showed that. So another thing I want to talk about is I've spent a lot of time talking about the low levels of smart contracts today and how to build these. Now, there are others that are building stuff on top of this, and Reach is a fascinating one, because what Reach does is it obfuscates all of the stuff I just told you and allows you to write business logic into an application, and it turns around and implements all the smart contracts that are required down below. It also formally verifies mathematically all the contracts that they use as well. So it's a really interesting language and framework, and its syntax is very JavaScript similar, and so it's a really, really unique tool. We got a couple tutorials on it, and we're going to be doing, we'll probably start to have a lot more tutorials on this as well. But and it's also, we've got full documentation site, reach.sh, or is that sh? Yeah, yep. And then one other thing I'll say is we got boilerplate examples out there. This presentation is available. I'll show you where it's at in a minute. Example, stateless and stateful smart contracts. But there's a set of guidelines, and these look like this. These are guidelines so you don't screw up and lose money. Make sure if you're developing smart contracts, that you adhere to those guidelines, please. It cannot be said enough. All right, and then this presentation is available here if you want to take a snapshot of that. Or just go to our GitHub at Algorand and look for smart contracts. It'll be under there. All right, and then finally, obviously, if you're not part of Discord, please join it. And there's our documentation site. We also do office hours, and we're going to continue to do those for for the foreseeable future. We already had one on Reach. We're going to be having several of the other really interesting tools that are being built on Algorand show up. Like next week, I believe, is one of the builder frameworks. So it should be very interesting. Please join us if you'd like to come to that. So my email is jason@algorand.com. In addition, you can contact us on Discord. We're on that all the time. So ping us on Discord, and I hope you enjoyed today's session.